Well, hello, welcome again to Math 315, Analysis and Topology. This is the first recording of Chapter 9, and this and the next chapter are probably going to be the most technically difficult of the chapters we're going to look at. And you'll see from the tutorial problems that the sort of things we'll ask on this are not quite so hard, but I need to go through a fair bit of fairly interesting theory, I hope. So I'm going to return finally in the second last topic to the question of how to define or construct the real number system. So as we said before, the ancient Greeks once thought that all numbers, in inverted commas, were either positive integers, they didn't believe in negative numbers or zero, or ratios of integers, that is, fractions or rational numbers. And as I mentioned before, it came as a rather nasty surprise to discover that root 2 was neither of these types. That root 2 was in fact neither a whole number, nor was it expressible as the quotient of two integers. So we usually say that root 2 is an irrational number, and the set of all real numbers consists of all the rational numbers together with all the irrational numbers. Well, that's fine, but it's not a very useful way of defining the real numbers. Essentially, at school, you don't bother too much about being too explicit about what a real number is. You say a number is irrational if it cannot be written as a fraction, and you leave it at that. So, simply defining it that way is not particularly useful in higher mathematics. And if we define an irrational number as one which is not rational, then we're saying what it is not what it is. In fact, there was much confusion about the set of real numbers until the mid-19th century, when a more watertight definition, well, there are now several of them, was devised by Dedekind. In all we have done above, we've tacitly assumed that the real numbers exist. In fact, without the real numbers, many of the theorems we've stated and used are no longer true. For example, the function f of x is x squared minus 2. We looked at that function, we said, look, it's continuous, it's negative at x is 0, you put x is 0 in, you get minus 2. It's positive at x is 4, you put 4 in, you get 14. So according to the intermediate value theorem, there should be a 0 for this function in the interval 0, 4. Well, that is not true if we don't have the real numbers, because the obvious 0 of this is at root 2, and so we need the real numbers for this theorem to be true. Now, there are a number of different possible approaches to constructing the real number system, and we'll have a look at a couple of these in some detail. Firstly, we can define them into existence. This method involves writing down all the axioms or rules which the real numbers obey, or which we would like them to obey, and then claiming there's essentially one set of numbers which obey these rules. And I will write down all the rules a little bit later to show you what all these rules and axioms are. Well, this raises a problem not only of existence but also of consistency and uniqueness. So even if I give you a set of rules, how do you know there is such an object that obeys all the rules? How do we know that these rules are consistent? They don't necessarily lead to contradictions. And how do we know there's only one system? So I will give a list of all the axioms a little bit later. The second one is to take a constructive approach, and one can use things called continued fractions to define real numbers. So, and we'll have a look at continued fractions at the end of this section. Won't be doing too much with them, but I'll show you how we actually get these things. So you can prove, in fact, that you can write root 2 as 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over forever. In other words, we can write this as these nested fractions, but going on forever. And we could then define root 2 as the limit of this object here, as you keep taking more and more terms here. Now, it turns out that the continued fraction of a rational number terminates. That is, it doesn't keep going on forever, it stops somewhere. and that's true if and only if the number's rational. Well, this again is fine, but of course we'll see later if you try and get the continued fraction of, say, pi, you can do it, but the numbers are very complicated and there's no pattern. So this method, in fact, was used by Omar Khayyam very early in the piece, about 1100 AD. The main difficulty with this method, so defining the continued fraction as defining real numbers in terms of continued fractions, is how do you add two continued fractions together and how do you multiply them? Well, that is next to impossible question, which I don't think there's never been any sensible answer to. So the third way of doing it, which is what you do basically in high school, at high school you simply think of things in terms of numbers in terms of decimal expansions. So you think of a rational number as the numbers whose decimal expansion either terminates, like 0.5 is a half, or is eventually repeating. So things like 1/3 is 0.33333 repeating, or 1/6 is 0.16666, so eventually it repeats. So the set of all real numbers then consists of the set of all decimals. That's what you do basically at high school to introduce real numbers. A fourth approach, which is more sophisticated, is using Cauchy sequences. We have mentioned those before, but what one does here is to consider the equivalence classes of Cauchy sequences. This is all rather technical, and we've seen that in the real numbers. All Cauchy sequences converge to some real number, so we can define real numbers using this idea basically, but it's complicated and a bit technical. The fifth approach is to use, which goes back to Dedekind, whom I mentioned before. It's called Dedekind cuts, and we'll have a little bit of a look at these Dedekind cuts. All the methods above effectively attempt to describe irrationals in terms of or as approximations to rationals. So intuitively, a Dedekind cut is going to be just an interval going from -infinity up to a, but excluding a. It's going to be an interval like this, and that will represent the real number a. Now, before we get to the idea of a Dedekind cut, we need to introduce some quite important ideas that I've delayed in the course until now, and this is the idea of least upper bounds and greatest lower bounds. So in order to try and make sense of the real numbers, we need the concept of least upper bound, sometimes called LUB, least upper bound, the LUB, and the greatest lower bound, which we're going to write as GLB. We'll have other names for them as well, but LUB, least upper bound, GLB, greatest lower bound. So to motivate our discussion, we're going to consider the set K, which consists of all numbers x, where x is strictly less than 0. And of course we can draw a picture of this. This is just this interval going back from 0, but excluding 0, and all the numbers going backwards. And we ask the question, does K have a greatest element? That is, can we find an element of K that is bigger than all the other elements in the set K? Can we find a number K that's bigger than all other elements in the set K? Well, clearly the answer then is no, because if I picked a number K somewhere, a little k in this set, and I said, oh, that's the greatest element, then since K is negative, the number K over 2, so think of K, for example, as -2, if I take a half of that, I get -1, and that's going to be larger since K is going to be less than K over 2 on the number line. So as soon as I say I've got a greatest element, then I will say, well, I'll take a half of it, and then I've got another element that's greater. Remember, we're excluding 0 here. So K has no greatest element. Now you might want to think about that, what I've just been saying here. If I claim there's a number k, I just take a half of that, and then I've got a bigger number, which is still in the set, but it's bigger than the one I claimed was the biggest one. So k has no greatest element. On the other hand, there's something special about 0 here, because everything in this set is less than 0, but 0 doesn't belong to the set itself. We excluded 0. So on the other hand, every element of k is less than the number 0. The trouble is, of course, that 0 is not in k, but it clearly plays a really important role in relation to this set k, in the sense that, even though it doesn't belong to k, every number in this set is less than this number 0 on the real line. So we're going to call it the least upper bound of the set k. Another name for it is to call it the supremum of the set k. So there's another new word, supremum. And we're going to write that as sup of k is 0. I'll give a technical definition of this in a moment, but just purely geometrically, we see that every number in k is less than 0, but 0 itself doesn't belong to k. We're going to call that the least upper bound of, or the LUB is the other word symbol we'll use, of this set, and we generally call it the supremum of k, or the sup of k. Okay, we've got that idea in our heads. Then we'll give a more formal definition of what we mean by this. Firstly, we want to define what we mean by an upper bound, and then we'll talk about the least upper bound. So given a subset A of the real numbers, so we just think always in this, just think of intervals along the, they don't necessarily have to be intervals, by the way, they could be more complicated objects, but in fact they could have holes in them or whatever, it doesn't matter, but it's convenient just to think of these at the moment as, just think of them as intervals. So given a subset A of the real numbers, a set X is called an upper bound if X is bigger than A for every element in the set A. In other words, looking at the line here, there's my set A, here's my X here. There's my X. Now X is an upper bound. It's not the smallest one, but it is an upper bound. What that means is that this X here is bigger than any A in the set we pick. This one is bigger than it. It is called an upper bound. It's not unique. I could have put X here, I could have put X here, but as long as it's bigger than every element in the set, then X is called an upper bound for the set A. Similarly, a number X is called a lower bound if X is less than every element of A. So I could also put my X here. Don't like using the same symbol twice, but anyway, put my X here. This is a lower bound. This is less than every element of A. So again, it's not unique, it is a lower bound. I could have put the X there or there, and it's still a lower bound. Now, of course, we don't want just any old upper bound or any old lower bound. We really want to talk about a least upper bound or a greatest lower bound, this supremum that I mentioned before. So again, think of it in terms of open intervals is easy here. So given a subset A number M is called the least upper bound, or the supremum is the fancy name we're going to use, of A if M is an upper bound for A. So there's, we think of M as being this point here, which is not in the set. It could, by the way, it could be a closed interval, it could be in the set, that's possible as well. But M is an upper bound for A, that is, all the elements here are less than this number M. If I say that X is any other upper bound for A, then M is less than X. So if I give you another X here and say, well, look, this X is an upper bound for this one, well, my M is also an upper bound, but M is less than X. And such a number we're going to call the least upper bound or the supremum, and we're going to write m is the sup of a. Again, it's convenient just to think of open intervals here, just to get the idea in your head, but in fact it's much more general than just open intervals. We can talk about the supremum of any set of real numbers, not necessarily just intervals. Well, similarly, given a subset A, a number little m is called a greatest lower bound, GLB, or we're going to use the word infimum. So I've got two new words, supremum for the least upper bound, and infimum, careful how you spell it, for the greatest lower bound. And that will be the case if, again, m is up lower bound for m, and if I give you any other x, so there's my little m here in the picture, again, convenient to think of it in terms of open intervals, but not the only set we could have. And then if I give you any other x, x is a lower bound for a, it's less than all the elements of a, but x is less or equal to this number m. So if I've got any other lower bound, then it's less than my greatest lower bound. And the notation here, we're going to write m equals inf of a, the infimum of a. Now, probably a good idea to have a look at a couple of examples here to cement this in. And so here's a couple of examples. We're going to let A be the set of, this is all real numbers. We take 1 minus 1 over x, and x is any number strictly bigger than 0. And we want to find the supremum of this set. And then for part B, we take 1 plus 1 over x, where x is any positive number. And we want to find the infimum of this set. And so I'll go through these examples here. So here's my set A, which is 1 minus 1 on x, x positive. Now again, it's a good idea to draw pictures here. So this says you take 1 minus something positive. So there's 1, and when you subtract something, if x is bigger than 0, then this is positive, and I'm subtracting it off, so I'm going to end up 1 minus x for some particular x is going to be here. So for example, if x was 1, then I would have the point 0. If I put x as 1, 1 minus 1 is 0. Now x could be small, so I could put x as a half, for example, and 1 over a half is 2, and that would give me the number minus 1. And so if you think about it, you're going to get all the numbers going backwards this way. It's 1 minus something, and that something can be positive. And so we're going to get all numbers, all real numbers back this way, but we're not going to get 1 itself. We won't, it's always 1 minus something. It's just a little bit less than 1. On the other hand, I could put x to be 100 in, and that would be 1 minus 1 on 100, which is 99 on 100, which is very close to 1, but never equals 1. So we can see from our picture that the supremum of A is going to be the number 1. 1 does not belong to the set, but every number in the set is less than 1. So 1 is an upper bound, and indeed it's the least upper bound, and hence the supremum. So that's a good example to think about. Example the other way, we're going to have a look at the set A as 1 plus 1 on x, where x is positive. This time we're taking 1 and we're adding something positive onto it. And again, draw a little picture here. So here's 1, and we're going a little bit further. We're adding something on, so we're going to be bigger than 1. And again, x, for example, could be a third, and then 1 over a third is 3, so that would be up here at 4. And by making x very close to 0, then this will be very big, and I can make this as big as I like, so I'm going to get all the real numbers this side. But it's always 1 plus something, so I never get to 1, but I get as close as I like. And again, if I put x as 100 in, then I'll get 1.01, so I'm just on this side of 1. So the 1 is a lower bound for this set, and in fact it's the greatest lower bound, and we call that the infimum, and we write inf of a equals 1. And I'll continue with this idea in the next recording.